And once we solve the Schrödinger equation for the oscillating atoms, we can talk about Phonon statistics. So we shall discuss here the calculation of the free energy. All right, so the total Hamiltonian of the system of oscillating atoms, as we have just discovered, is given by the sum of Hamiltonian associated with each individual normal mode, lambda, and that Hamiltonian is given by that expression, where n lambda is an operator associated with the excitation number n lambda of the oscillator. And you may have had in the course of your statistical mechanics that this n lambda is actually given by a product of two ladder operators, a dagger and a, corresponding to the excitation of an oscillator. The eigenvalue of this operator n lambda is that number n lambda which we introduced above. It's an integer number. So this n lambda as an operator has as an eigenstate n lambda, which corresponds to all possible collections of these numbers for each oscillator, and its eigenstate is n lambda like this. So if our collection of oscillators would have a particular set of all these numbers in lambda, when we act with the operator n lambda on that state, we obtain that state multiplied by this integer depending on how many oscillators of this type lambda are excited. The Helmholtz free energy can be obtained from the partition function z in quantum statistical mechanics, and kBt is the temperature. So z, the partition function or statistical sum, is obtained as a trace of the e to the minus beta h operator, and beta is the inverse of kt. But because the Hamiltonian is the sum of Hamiltonians, which are completely independent of each other, this exponential operator can be written as a product of exponential operators for each particular lambda, and therefore the statistical sum can be written as a product of statistical sums for each oscillator, in which z lambda, the statistical sum for the particular oscillator lambda, is given as a trace of this operator e to the minus beta small h lambda, where this h lambda is given here. And this statistical sum can be easily calculated. Indeed, what we need to do, we need to sum over all possible states and take these matrix elements. But because n lambda is an eigenstate of the operator n lambda, and h lambda is just a linear combination of that operator with a prefactor and a constant, of course, these n lambda are eigenstates of h lambda as well. And therefore, when we calculate this matrix element, it will be equal basically to that exponent in which h lambda is replaced by the eigenstate. So here we have n lambda as a number, and we sum over all possible states of an oscillator when this number changes between 0 and infinity. This is how many excitations you may have, or how many occupancy each oscillator may have, starting from 0 at the ground state and coming up to any number up to infinity. This is the geometric progression, can be calculated exactly. This is the result. And because of that, one can easily calculate the free energy of the system of harmonic oscillators. For that, we take this z lambda, substitute it in here, so we get the full z, the full partition function, and we take the logarithm of it here, and this will be my free energy. So I use this expression, then replace z lambda with this, and after some little algebra, we arrive at that expression. So this is an exact expression for the free energy, exact quantum mechanical expression for the free energy of a collection of harmonic oscillators. You see, it consists of a constant term, which is called 0-point energy, and a temperature-dependent term. Temperature comes in here, in front of the logarithm, and also in this beta. The free energy calculated like this corresponds to the so-called quasi-harmonic approximation. The reason for this terminology is because with this technique, we should be able to study, even though we use harmonic approximation, we will be able to study thermal expansion as well, which is due to unharmonicity. So in the harmonic case, the potential energy surface is parabolic, and therefore it is fully symmetric with respect to the equilibrium position, the minimum of the potential energy surface. However, we know that in reality, potential energy surface is not symmetric, and it is going differently, less steep, as we go towards larger distances. You may wonder how the quasi-harmonic approximation may help in studying this thermal expansion, because this is the reason for the thermal expansion, right? So we have oscillations of atoms as the temperature is increasing. The oscillations cover more and more distances, and the average position of oscillating atoms would tend towards larger distances, interatomic distances, which is the physical reason for the thermal expansion. So in order to study thermal expansion, what one can do using this approximation is to consider a particular volume of a crystal. Let's take as an example, because it's the simplest example we can consider, of a cubic crystal. Cubic crystals could be either of a simple cubic, FCC or BCC, Bravais lattices, but in all these cases, just a single parameter, interatomic distance or a lattice constant, would determine the volume of the primitive unit cell. So we take a particular lattice constant, and for that lattice constant, we relax atomic positions. This needs to be done only if there are more than one atom in the unit cell, of course. So then we determine the DFT energy of that structure. Then we calculate vibrational frequency at that structure. We can always do this because the linear term in the expansion of the total of the potential energy with respect to atomic displacements would be still zero. And then calculate from these vibrational frequencies for the given temperature and volume of the crystal. We shall calculate this contribution of vibrations into the free energy. So this way, by summing up these two terms, we calculate the the free energy of the crystal as a function of its volume or lattice constant and the temperature. Then for the given temperature, we can determine the minimum of this free energy. This would give us the volume of the system or lattice constant for that particular temperature. Then calculation is repeated for another temperature. No new DFT calculation of the vibration frequencies is required because they depend on the volume of the unit cell. So we can just use the data we already have. And we can determine the volume, the minimum of the free energy, and therefore the volume, and at a different temperature. In this way, we can approach that problem of thermal expansion. So we use harmonic approximation in expanding the potential energy of a crystal with respect to atomic displacements. However, in a more general sense, we are able to go beyond the harmonic approximation and study thermal expansion. That's why this kind of approach is called quasi-harmonic approximation. It's not entirely 100% harmonic. Of course, this consideration was made for a cubic crystal. In the case of a non-cubic crystal, there will be more than one parameter to determine the unit cell, the shape, maybe and the size of the unit cell, primitive unit cell. In that case, The same can be said, but in this case the calculation will be much more complex. For instance, if you take a rectangular unit cell, you would have three parameters, A, B, C, along the x, y, z direction. So you will, instead of a single lattice constant, you will have three lattice constants. So you will have to determine the minimum of the free energy as a function of three lattice constants. And for each value of the lattice constant, you will have to calculate the DFT energy and determine all the vibrations. This computation is extremely expensive. So the case we considered so far corresponds to the zero pressure. This is the case of the NVT ensemble, when the volume is fixed, temperature is fixed, and the number of particles is fixed. And within that ensemble, we determine the equilibrium structure. What is the equilibrium volume for that temperature? If, however, the pressure is a constant, so we have to use NPT ensemble instead. In that case, the correct thermodynamic potential is not the free energy, but the Gibbs free energy, which is related to the Helmholtz free energy F, which we used so far, by an extra term PV. In that case, the equilibrium structure for the given pressure is calculated as a minimum of that free energy, or in other words, by differentiating G with respect to the volume at a constant temperature and setting it to zero, you will find this particular relationship between the Helmholtz free energy and the pressure. So if in the previous case of the NVT ensemble constant volume, we determined the minimum of the free energy with respect to the volume. So here in the right hand side we had zero. Now we simply have minus pressure. So this theory, as you can see, allows us to study thermodynamics of crystals to determine the equation of state, either in NVT or NPT ensembles.